In this tutorial, we're going to take a look at the answers to a test review on trigonometry. And this is for the Advanced Functions course in the province of Ontario, Canada. And this trigonometry is all the special angles, some applications, trig identities, but no functions stuff at all for the trig unit. That's in another test. In this course, the way I teach it, I divide it into two different parts. And so we're going to start with some multiple choice here. First of all, in number 1, it says the cosine of 5 pi over 3. And we're going to move over to my unit circle here. The way the unit circle works is the radius is 1, so there's 1 unit. That's why that's 1, 0, or negative 1, 0, or 0, 1 up here. And it's the counterclockwise rotation from 1, 0. And so we're looking for, in the first one, the cosine of 5 pi over 3. So that's the angle. So we need to find 5 pi over 3 here. And there's the 5 pi over 3 angle. So it's the rotation, again, counterclockwise, all the way around to that point. And this is the point that goes with that. So it's the point right after where you see the angle listed. Now, cosine is the x-coordinate. So we're looking for the cosine of 5 pi over 3. So that would be 1/2. The sine of 5 pi over 3 would be negative root 3 over 2, the exact value. So 1/2 is answer B, so that's the correct answer for number 1. The tan of 11 pi over 6. Now, we don't read tans, cotans, secants, cosecants directly from this, but we can use the sines and cosines to find each of those. So you do need a little bit of identities in a few of these questions. So for example, the tan of an angle is the sine of the same angle divided by the cos of the same angle. So I need to scroll down here to my 11 pi over 6, which is right here. And so the tan of 11 pi over 6 would equal the sine of 11 pi over 6, which is this negative 1/2, divided by the cosine of 11 pi over 6, which is this root 3 over 2. So that's why I'm dividing those. Now, the 2's in the denominator would divide out, and so the answer would be negative 1 in the numerator, so negative 1 over root 3. So if we go back to our answers, negative 1 over root 3 is answer A here, so that's the correct answer for question number 2. Now, one little note before we go on to the next one. You could have a slightly different version of this answer in a multiple choice somewhere. And there's a process called rationalizing the denominator. So I'm going to multiply by root 3 top and bottom because of the fact that the denominator had a root 3 in it. And so this process, actually, when you multiply root 3 by root 3, you get 3. So it's called rationalizing the denominator because it changed the denominator into a non-irrational number. Okay, it's a rational number. 3 is a rational number. A rational number. Negative 1 times root 3 on top would be negative root 3. So that is an equivalent answer. So you could have a multiple choice that it might have that for an answer. Question number 3, the cosecant of 7 pi over 6. And again, you can't read cosecants directly from that unit circle, but cosecant and sine are reciprocals. So I'm going to go back here, and it's 7 pi over 6, remember? Okay, that's the angle I'm looking for. So I need to read the sine of 7 pi over 6 from the unit circle. So again, here's 7 pi over 6. So it's this point I'm looking for, and it's the sine. So negative 1/2 would be the sine of 7 pi over 6. So this equals negative 1/2. And the cosecant and the sine are reciprocals. So we need to take the reciprocal of this and need to flip it upside down. So it's still negative. And so it would be negative 2 over 1, which of course simplifies to negative 2. And so that's why D is the correct answer for question 3. For question number 4, to convert radians to degrees, multiply by. And a lot of people recognize that it's going to be either answer B or answer E. Pi and 180 are equivalent. Pi radians is 180 degrees. Now, if you're not sure to remember which order it is the pi on top, is the pi in the bottom? Okay, here's a way to remember. So let's say I was taking the 7 pi over 6, and I was going to convert it into degrees. Okay, so that's what the question is asking. Okay, what do we multiply by? See, the 180 has to be 180 degrees. Has to be in the numerator because, so it's 180 over pi, because if I'm going into degrees, the pi's have to divide out. Okay, so that's how I know the pi, how I remember the pi is going to be in the denominator, because it's going to divide out with that pi from the angle in radians. And so that's why B is the correct answer for question number 4. Number 5, if the radius of a circle is r, radius is r, and the angle of the sector is beta, and it has to be in radians. If it's in degrees, the formula is slightly different. Then which is the formula for the length of the arc along the circle? Glancing at the answers, this is actually the area of a circle formula, so that certainly wouldn't be right because it doesn't even have an S here. The other 4 do. E is the correct answer. Arc length is just the radius times the size of the angle in radians. That's all you have to do. It's a very simple little formula for arc length as long as the angle is in radians. If the angle is in degrees, again, then it's a different formula. Number 6, which of the following is equivalent to the sine of 4 pi over 3? So, and we've got several, we'll start looking at these. So, sine of 4 pi over 3, okay, here's my sine 4 pi over 3, so I have to locate the 4 pi over 3, and there's the angle there. So the rotation is all over around to that point, and the sine would be negative root 3 over 2. So I'm really looking for which of these is equal to negative root 3 over 2. Okay, so I'm going to write that down. So we can go back and start looking at angles. So the sine of pi over 4. So let's find the sine of pi over 4. See, the sine of pi over 4 would be this. So that's certainly not negative root 3 over 2. So that can't be the correct answer. The tan of 3 pi over 2. Now, here's 3 pi over 2 down here. The tan would be the sine value divided by the cosine value. If I divide negative 1 by 0, you can't actually do that because you can't divide by 0. So the tan of that's undefined, so it certainly isn't negative root 3 over 2. The sine of 5 pi over 6, is that correct? The correct answer. So 5 pi over 6. So 5 pi over 6 is the angle around to here. So rotating around to that, 5 pi over 6. The sine of 5 pi over 6 would be a half, so not the same as this. So C is not the correct answer. D, the sine of 11 pi over 6. So let's find 11 pi over 6. We actually were looking at that a moment ago, the sine of 11 pi over 6. So the angle rotates around to here, so the sine value would be negative a half. That's not correct. That's not the same thing. Cosine of 5 pi over 6. So 5 pi over 6 is here. Okay, so we rotate around to here. The cosine of that would be negative root 3 over 2. Oh, there's the one. It is the same as this one. So that's why E would be the correct answer. The sine of 4 pi over 3 and the cosine of 5 pi over 6 are the same. They're both negative root 3 over 2. So E is the correct answer for question number 4. Number 7. The cosine of negative x, negative rotation. There's a couple of rules for cosines and sines of negative x, and cosine of negative x is the same as cosine of x. And I'm going to go back to my unit circle one more time here just to explain why that is. So, for example, let's say the angle was pi over 3. And its cosine, okay, so go back, it's cosine. So cosine is the x coordinate, remember. So the cosine of pi over 3 would be a half. If I rotate the same amount as that in the negative rotation, so this is the negative rotation, takes me down to that point right there. Notice that the cosine half is the same as the cosine up here. If I rotate to pi over 4, cosine's root 3 over 2. If I rotate the same amount in negative direction, I get the same cosine value. And it works over in the other quadrants too. See, if I rotate, let's say I rotate around to here, 5 pi over 6. The cosine's negative root 3 over 2. If I rotate, see, the same as that in a negative direction, so I would rotate around to here, okay, see, negative root 3 over 2, same as that cosine value. So the cosine of any rotation and the opposite rotation are the same. So that's why cosine of negative x is the same as cos of x. So B is the correct answer for question number 7. Not the same is not true with sine, but that's a different question. In part 2 here, These are the questions where you start showing some work. So in A here, we're asked to convert that 7 pi over 6 into degrees. So we multiply by 180, so those pi's will divide out. That's why I have those crossed out. The 6 goes into 180 30 times, and then just 7 times 30 would be 210. That's not an exponent, it's just 180 divided by 6 is 30. So 7 pi over 6 is the same as 210 degrees. In B, we're asked to convert 3 pi over 20 into degrees. So again, I multiply by 180 over pi, so the pi's divide out. 20 goes into 189 times, so 9 times 3 would be 27. So 3 pi over 20 would be 27 degrees. Question number 2. The radius of the Earth is 6,380 kilometers. Some space junk, 375 kilometers above the Earth, travels around the planet through an angle of 4 pi over 3 radians. And you're asked, how far does the space junk move to the nearest kilometer through this rotation? So remember, the radius is 6,380, but you see we're actually above it a bit. We're 375 kilometers above it. So see, this would be the Earth right here, and this is the orbit of that space junk, 375 kilometers above the Earth. So in order to get the radius of the orbit for that space junk, we'd have to add this 375 to the 6,380. So the R value would be the radius of the Earth plus how much it is above the Earth, the 375, which is 6,755 kilometers. So that's the rotation. So from the that multiple choice question, remember arc length is the size of the radius times the angle in radians. So the radius is the 6,755 over here times the 4 pi over 3 radians, and so we get 28,295 kilometers. So there's the actual calculation from my graphing calculator. To nearest kilometer, of course, the 0.277 would make it round down, so we keep the 95, and there's the distance it would travel through that rotation. Question number 3. Evaluate the following, leaving an exact form only. So we've got cosine pi over 3 times the sine of 4 pi over 3 divided by the tan of 11 pi over 6. So I would go back to my unit circle to find each of these. So cosine pi over 3, first of all. Cosine pi over 3 would be a half. So that's where this half comes from. Now we need the sine of 4 pi over 3, so back to my unit circle. 4 pi over 3 is here. That would be the sine value, negative root 3 over 2. So that's the negative root 3 over 2. And then divided by the tan of 11 pi over 6. Now remember, we actually did that one, the tan of 11 pi over 6 in the multiple choice. Tan of 11 pi over 6 would be the sine of 11 pi over 6 divided by the cosine of 11 pi over 6, which was this negative 1 over root 3 or negative root 3 over 3. You could use either of those. So I use the unsimplified one, the same one from the multiple choice answer. And so negative a half divided by the root 3 over 2. Remember, the 2's divide out. You get negative 1 over root 3. So that's where that comes from again. And up on top here in the numerator, 1 times negative root 3 would be negative root 3. 2 times 2 is 4. So it's negative root 3 over 4 when you multiply that sine and cosine together. And so in order to simplify this, I take the numerator expression and multiply it by the reciprocal of the denominator. And so that would be negative root 3 over 1. Now, a negative times negative is positive. Root 3 times root 3 is 3. You get the root of 9, which equals 3. And in the denominator, 4 times 1 would be 4. So 3/4 is the exact value of this expression. Question number 4 says use a compound angle identity to prove that the sine of x plus pi over 2 is equal to cosine of x. So since this is the sine of the sum of two angles, x plus pi over 2, in terms of identities, we often call it A and B in the trig identity sheet. So then I would use the A and B, or x and y. I would use the identity sine x plus y equals sine x cos y plus cos x sine y. On the identity sheet, it looks like this. The sine of A plus B, is A's and B's here, is sine A cos B. Now, if it's plus, see, we use this plus, and then cos A sine B. Now, of course, we can change this to x and y's, just as I have in the solutions here. So that's the identity that I'm using. And so I'm going to replace pi over 2 with the y. That's x, and this is going to be y here. So the sine of x plus pi over 2 would be, so it's sine x, and then the cosine of pi over 2. That's the second angle, so instead of cos y, it's cos pi over 2. And cos x at the beginning here, and then the sine of y. Again, y is the pi over 2 here. So that's what we have on the end. So now what we need to do is go to our unit circle and evaluate the cosine and sine of pi over 2. So cosine of pi over 2, pi over 2 is here. The cosine value is 0. So that's why this becomes 0. And then the sine of pi over 2, the sine of pi over 2 is 1. So that's why we can substitute a 1 in place of this. Now 0 times sine x would be 0, so that part's gone. And the cos x times 1 is just cos x. So the sine of x plus pi over 2 simplifies to just cos x. Question number 5 says use a compound angle identity to rewrite cos 7 pi over 12 times cos pi over 4 minus sine 7 pi over 12 times sine pi over 4 as one single trig ratio, not a product of two and then subtracted, as one single trig ratio, and then find its exact value. So since the expression here goes cos times a cos minus sine times a sine, okay, so since it looks like that, then we would use the, we're looking for one that has cos times a cos minus sine times a sine, which is the cos x plus y one. If you go back to your trig identity sheet, it's this one here. So going back here again, cos times a cos minus sine times a sine. So it's cos times a cos minus sine times a sine. So that's the identity that we're using, and we have its minus. So that's the cos a plus b one, or what I have written on the solutions there is using x and y, but it's minus in the expression, so we use the sum of two angles one. So the identity that we want is cos x plus y equals cos x cos y minus sine x sine y, and so this is going to be 7 pi over 12. And the y here is going to be the pi over 4. So if this is 7, so we have 7 pi over 12, and then cos pi over 4, and then minus the sine of 7 pi over 12 times the sine of, and y is the pi over 4. So we're kind of using this identity in reverse, because we've got this expression at the beginning, that's what we're starting with here, and we're going to simplify this into the cos of x plus y. So this is this part over here. And so this will all simplify like this does to equal the cos of the sum of x and y, cos of x plus y. So here's the cos of x plus y. And again, x is 7 pi over 12, y is the pi over 4. In order to add those, I want a common denominator. So the first thing I would do over here is I'd multiply this pi over 4 by 3 in the numerator and denominator. And so that becomes 3 pi over 12. So 7 pi over 12 and 3 pi over 12 would add to 10 pi over 12. And you can divide 2 into both of those, so reduce to 5 pi over 6. So this whole thing is the same as the cosine of 5 pi over 6. And if we want its exact value. So this is the simplified into one trig ratio. Okay, so the product and difference of all this is the cosine of 5 pi over 6. And then we go back to our unit circle over here. 5 pi over 6 is this, and it's the cosine, so it's negative root 3 over 2. So that's why negative root 3 over 2 is the exact value of all of that. Question number 6. Determine the exact value for the sine of 19 pi over 12. Now, there's often a lot of different ways you can do these. I'm going to show you one and then show you a little bit of how another way you could do this. So we're asked to find the sine of 19 pi over 12. And so I would want to take all those angles, not all those angles, but a lot of them. I did all the ones in the first two quadrants. And I got a denominator of 12 for all of them. So I'd multiply like these two by 2 in top and bottom, the 4s by 3, the 3's by 4, that one by 6 top and bottom. And so I wrote a whole bunch of those out on the side here. And what I'm looking for is two angles that would add up to 19 pi over 12. And so, for example, the reason I stopped here is because you see 9 pi over 12 and 10 pi over 12 would add to 19 pi over 12. So, and those are the ones I actually used here. Okay, so see, I need two angles that add to 19 pi over 12. If you use the sine x minus y, and you can do that too, then you would instead want a little larger angles, or at least the biggest one, so that they would subtract to 19 pi over 12. Now, those aren't only two angles that add to 19 pi over 12. So, for example, here's another, if I kept the list going a little further, and down, if I went to like 5 pi over 4. If I multiplied that by 3 top and bottom, that would be 15 pi over 12. And so, see, 15 pi over 12 and 4 pi over 12 would also add to 19 pi over 12. So I could have used pi over 3 and 5 pi over 4. That's another of many ways you could do this. So now looking at the one I actually did use. So the two angles are 3 pi over 4, 3 pi over 4 and 5 pi over 6. Those two add to 19 pi over 12. So that's ones I'm using in place of x and y here. So if I'm using the sine x plus y identity, it's sine x cos y plus cos x sine y. And so I'm putting in place of x the 3 pi over 4, in place of y the 5 pi over 6, so that's why the sine of x plus y becomes this. So 3 pi over 4 goes here, sine 3 pi over 4, and cos 3 pi over 4. And the y is 5 pi over 6, so 5 pi over 6 here, 5 pi over 6 here. And then it's a matter of looking at the unit circle. So what are all these sines and cosines? So the sine, actually let's do the 3 pi over 4. We need the sine and cosine, those two both. So 3 pi over 4 is here, so the sine is root 2 over 2, and the cosine is negative root 2 over 2. Okay, so the sine is root 2 over 2, and the cosine is negative root 2 over 2. Now let's do the cosine and sine of 5 pi over 6. So 5 pi over 6 is this angle right here, okay, right next to it. So the cosine is negative root 3 over 2, and the sine is a half. So back here again, the sine is a half, and the cosine of 5 pi over 6 is a negative root 3 over 2. And so I do my little bit of multiplying here. Root 2 times root 3 is root 6. It's negative here because we have one negative in that product, and 2 times 2 is 4 in the denominator. Negative, so we have a minus here. Root 2 times 1 is root 2. 2 times 2 in the denominator is 4. Have a common denominator, so we could just write this as, now, I did a little bit of minor factoring, I suppose. You could write it as negative root 6 minus root 2 over 4. That is correct. But what I actually did to write my final answer is, because these are both negative, I factored a negative 1 out of that. So, and if you do that, don't write the negative up here because it'll make it look like only the root 6 is negative. The whole thing is negative. It's like factoring a negative 1 out, really. So it's negative root 6 plus root 2 over 4. And question number 7 here has to prove any two of the following three identities. So I'll go over all three of them. So on the first one here, at A, it's sine x cos x tan x equals 1 minus cos squared x. And in the identities, it's okay to work with the two sides independently. Sometimes you can take one and make it look exactly like the other. But as long as you show they're both equal to the same thing, that's okay. I usually start with the larger, more complicated side. That's usually sort of a guideline. Doesn't always work the best, but it works a lot of the time, probably 80–90% of the time. So that's why I'm starting with the sine x, cos x, tan x side on the left here. So my left side is that. Good mathematical form, write that down and start working with that side there. Now, I have my identities here, and we're using mostly these ones up here. So sine x, if you see a tan, and sines and cosines in the same thing, it's usually a good idea to change the tan into a sine x over cos x. So that's what I did from here. I changed this tan into sine x over cos x, and then these cosines divide out, so I'm left with sine x times sine x, which is sine squared x. Now, back to the trig identity sheet here for a moment here. Pythagorean relation, sine squared, well, theta plus cos squared theta equals 1. I wrote it as sine squared x plus cos squared x equals 1 because x is my angle here. And if you rearrange this, if we subtract cos squared theta from both sides here, so if we do this, cos squared, I said theta, I think I meant x, cos squared x. So those add to 0, so sine squared x is equal to 1 minus cos squared x. So this is equal to 1 minus cos squared x, which is, again, keep an eye on that right side. That's what we wanted to show, it's equal, and so my identity is complete. This is equal to the right side. Make sure you have a concluding statement, therefore sine x cos x tan x is equal to 1 minus cos squared x. Another common way to end a proof is to write this at the end of a proof. It's Latin for quod erat demonstrandum, which simply means that I have proven what I set out to prove true. Question B here. Sine squared x plus cos squared x plus secant squared x equal to 2 plus tan squared x. Again, the left side is the longer side by a considerable amount here, so that's why I'll start with the left side. So here's my sine squared x plus cos squared x plus secant squared x. And again, from this identity up here, remember sine squared x plus cos squared x equals 1. So I can change all this into 1. Now, keeping an eye on the fact that I want to show this is equal to 2 plus tan squared x. So I need an identity. I need to get my secant squared, no longer a secant squared, but a tan squared. So I'm going to go back here to this, actually, it's not on that sheet, is it? It's another Pythagorean relation that's not there. Go back to the test here. And the identity looks like this. I'm going to pause for a second and write it out. And so there's my identity. So secant squared x is equal to tan squared x plus 1. So in place of the secant squared x, I can put tan squared x plus 1. And again, this is my right side. I want to show is equal to that. So when I add the two ones together, that's the 2 there. And then I have tan squared x. So that is equal to 2 tan squared x, so it equals the right side. So we're done. So this does equal this. So there's my concluding statement, or QED. C, the last one here, and by far the longer of the three, are asked to show that 2 cotan x over 1 plus cotan squared x is equal to sine 2x. And again, when you see sines or cosines and tans or cotans, cosecants, secants, write everything in terms of sines and cosines. So cotan, okay, and so I'm going to start with my left side here again. So 2 cotan x over 1 plus cotan squared x. The cotan is equal to cos over sine. So cotan x equals cos x over sine x. Of course, it's multiplied by 2, so the 2 stays with the cosine in the numerator. In the denominator, cotan squared, which just means it's cos squared. Whoops, I'm looking at the wrong spot here. Cotan squared is cos squared x over sine squared x. Now, I'm adding that to the 1, so this is my denominator from here. So I would change that first and say, well, I've got a denominator of sine squared x. So that 1, I'm going to multiply it top and bottom by sine squared x. So that's why where that sine squared x over sine squared x comes from, I'm changing the 1 into it. Because I now have a common denominator here. So I left my numerator alone. So 2 cos x over sine x. In the denominator, see, I can add these because the sine squared x denominators are the same. So then it'll be sine squared x plus cos squared x, which is what I have here, over a sine squared x. And the reason I do that is because this, again, that's one of the most frequently used Pythagorean identities. Sine squared x plus cos squared x is 1. So I'm going to change this into 1. So this numerator, one more time, stays exactly the same. Actually, I guess not the last time. And in the denominator, sine squared x plus cos squared x is 1. So that's that 1 right there over sine squared x. Now, I'm dividing two rational expressions, so I'm going to take my numerator, the 2 cos x over sine x, which is what I have right here, and multiply it by the reciprocal of this denominator. That's how you divide rational expressions. You multiply by the reciprocal. So times, and the reciprocal of this would be sine squared x over 1. We'll scroll a little bit. So we've got a sine x here and a sine squared x. So there's two sines multiplied here. What I often do when dividing out like this sine x is gone. It's going to divide it with one of those signs, so I'll normally just cross out the exponent because there's still a sine x left there. And so what I have left is 2 cos x sine x, and that is equal to sine 2x. And that's actually on the trig identity sheet here. Sine 2x, or sine 2 theta, equals 2 sine theta cos theta. I'm actually using it in this direction. I'm changing this into this. So 2 cos x sine x is equal to sine 2x, which is what's on the right side. So it's exactly what I want. So that's equal to the right side. So therefore 2 cotan x over 1 plus cotan squared x is equal to sine 2x. And that's the end of the tutorial.